So I've started the recording. So welcome to the CSCS webinar, how to prepare the technical report for proposal submission. This is intended for the CSCS user community, and it will cover, as it is outlined here, both the user lab and the praise allocation schemes. So both the production project in the national user lab and the praise tier 0 projects. So this will be the first part of the talk, when we will outline the two types of calls that we have for big projects, production projects. And then we will go through a section that is dedicated to the technical part of the proposal. So what we call the technical report. We will show what is the proposal template and the performance analysis. And last but not least, we will follow an example step by step with a supported application using CRayPath for the national call, and then some additional technical guidelines for T0 calls. So let's go to the user lab allocation schemes. CSCS grants world-class resources to all researchers in Switzerland. So this is the usual problem is that HPC computing systems are always subscribed, and the competition keeps quality of science high. Then granted resources depend on the quality of the proposal. But then we ask scientific researchers to access CSCS computing resources by submitting proposals. The resources are given for free, but still you need to submit the proposal and you need to provide a technical report. Now, the scientific evaluation of the proposal is performed by international experts, while the technical feasibility is reviewed by CSCS staff. For the national calls of proposals, we have different type of allocation schemes. So we first start with the preliminary schemes that are preparatory projects. They can be submitted at any time. They can be approved in 72 hours at the minimum. Then they're used for porting and testing codes before applying for a production project, and to generate the mandatory technical report for production project proposals. We have also development projects that are meant to work on codes and algorithms to port the codes, for instance, on GPU accelerators. If you ask more than 36,000 node hours, then they also go through a scientific evaluation, a part of the standard technical feasibility assessment. If it is asking less than 36,000 node hours on the Cray XC50 as well, the technical evaluation is the only review that is performed. You can find more details at the link at the bottom of the page. Now, the biggest projects are called production projects, and they target simulations for a specific scientific investigation. They happen twice per year. The call is twice per year, with allocation periods starting on April 1st and October 1st each year. Researchers can only apply for resources on the hybrid Cray XC50, so the GPU accelerators, the nodes with GPU accelerators. And the technical report must be performed on the GPU partition, so running on the GPU nodes. You can find out more details at the link that I provide here on the page. Bear in mind that the next deadline is May 8th, 2020, and the allocation of successful applicants will start on October 1st. You can view all the next deadlines at the link at the bottom of the page. For praise tier 0 calls for proposals, we have started in 2017 as CSCS as a praise hosting member for tier 0 projects. Tier 0 are the highest level of HPC resources available. So praise is an acronym for the Partnership for Advanced Computing in Europe. The other hosting members are France, Germany, Italy, and Spain. They all have systems at tier 0 level that are part of the praise call for proposal. The CSCS user program in the past has been always open to scientists from around the world, and the participation of CSCS as a praise hosting member just extends this tradition. But this opens up new opportunities for Swiss computational scientists, as being let's say, Switzerland as a hosting member, give some kind of priority to access a European high-end computing infrastructures with diverse architectures to Swiss scientists. Now, also praise has different allocation schemes possible. So we start with the preliminary ones. In parallel with what we have, in a similar way, there are the so-called preparatory access projects of PRAISE. They can be submitted at any time, and there are two types of such projects. Type A, which is meant to generate the technical data for a Tier 0 project access. Successful project will receive limited resources, as in the case of CSCS preliminary projects. And type B, which is meant for development, code development and optimization performed by the applicant. Successful applicant will also have limited resources for a limited amount of time, maximum 6 months. And to access PITS-DINT with the type B preparatory access of PRAISE, you need to provide a development project with milestones that are clearly defined on the GPU nodes. You can discover how to apply at the link that I put at the bottom of the page. The main call for proposals for PRAISE Tier 0 allocations is the project access. The project is aimed at scientific projects with the need of large allocations. This happens as well twice per year, and the allocation periods start on April 1st and October 1st as the national call of CSCS. You must prove for this access the use of GPU accelerators on the hybrid Cray XA50, so the part of PITS-DINT with GPU nodes. And the proposal must additionally justify a resource request of at least 1 million node hours on PITS-DINT. You can find more information at the link in the page. The next deadline is April 28, 2020, with allocation starting on October 1st this year. You can apply at the link provided at the bottom of the page following the next call for proposals, that is call 21st. Now, let's go to the core of the talk, which is about the technical report. So the technical assessment of proposals is performed on both types of calls. The national calls for proposals, in which production project proposals are technically reviewed by CSCS staff, and the PRAISE Tier 0 calls for proposals. In that case, the project access proposals are reviewed by the staff of the PRAISE hosting member site that you have targeted in your proposal to assess the technical suitability of the proposal. In our case, since we're talking about PITS-DINT in this call, we are supposing that you apply in the Tier 0 call for PITS-DINT, and it will be still the CSCS staff to review the technical suitability of the project. Applicants may be contacted by the staff of the center during the review process. So keep that in mind, because you might be asked for additional items that are missing in the proposal. Now, let's go to the national calls for proposals first. So the technical report is the part of the proposal template that I put in the bottom of the page a link to the PDF, to the PDF pages of the proposal template. And the technical report is divided in different sections of the project template. There is a section called research methods, algorithms, and code parallelization, then representative benchmarks and scaling, performance analysis, and finally resource justification with the annual node hours and the disk space request. We are going through these sections now. So first, research methods, algorithms, and code parallelization. This section should include a description of the methods and the algorithms of the codes that you adopted. So you need to justify your choices and describe possible alternatives. You need to specify whether you are a developer or a user of the code. And you need to describe scientific libraries employed and the parallelization approach. So for instance, you need to highlight the specific memory and the I/O requirements of your code. And then there is a specific part that is for community codes, because community codes, so the codes that are used by large scientific communities, in general publish this information on the websites. Still, many users use a modified version of these codes. So in this case, please clearly state if you use a modified version and explain why you are not using the public available version, the version that is publicly available. And then instead, if you are not using a community code, then we suppose that you are either a developer or an advanced user of the code. So you should please describe in more detail the items that I've listed above. Next section is representative benchmarks and scaling. So this is done by performing a strong and weak scaling test with the code that you have selected and the specific representative system of your project. Now, if you cannot do both strong and weak scaling, you should still justify why only one of them is applied. And then we ask you to report the scaling data in a table and a scaling plot for each of the representative systems that you intend to study in your project. Now, the goal of the representative of the scaling of the representative system is to choose the most efficient node count that you will use to run the performance analysis. And this is supposed to be the node count, the number of nodes that you will use in your project during the production phase of your project when you will be starting your scientific study. So you need to select meaningful job sizes in order to simulate the representative systems, and possibly using short run times to avoid wasting resources just for that. In general, a few minutes should be enough for a standard benchmark for scaling. Typically, the lowest number of nodes that you run is determined by the memory and wall time constraints. So memory, of course, if you need larger memory, you cannot run on small nodes. If you need a memory that is larger than the memory available on the node. And wall time constraint, we are not advising to run for longer times, as this would really waste resources just for the scaling purpose. The highest node counts should let you identify the scaling limit. So once you go below the 50 parallel efficiency, let's say, because we always ask to target at least 50% parallel efficiency in the choice of your optimal node count. Let's see that how. So this is an extract from the proposal template. So you see on the left side, a small table where we have put the number of nodes, the wall time in seconds, a column with the speed up, and a column with job ID that is now, for the time being, it is empty. So this is how we assume you will present your data. The speed up is computed with a formula below at the bottom of the page. So the speed up on n nodes, it's computed by taking the reference time at the beginning of the scaling. In this case, we started with 2 nodes, so the time on 2 nodes. And then you divide by the timing, the wall time that you got on n nodes. Since the scaling is supposed to go faster, then you will have a number bigger than 1. The parallel efficiency on the same amount of nodes, n nodes, will be then the ratio of the speed up divided by the ideal speed up. When we talk about ideal speed up, we always talk about something that grows linearly. So you double the number of resources, the number of nodes, we are supposed to double the speed up. So to get a half wall time in order to get an advantage. So the ratio speed up divided by n halves, because in this time we have started with 2 nodes, will give you what is the parallel efficiency. In this particular example, you can see that at 16 nodes, we are more or less at 60% efficiency, ratio between the 4.87 divided by 8, which is 16 divided by 2. In this case, you can visualize that almost immediately in the scaling plot that is given on the right side of the slide. You can see that more or less at 16 nodes, we are a bit above the halfway with respect to the line that is the ideal speed up. And then if you go to 32 nodes, you see that you don't have any increase in performance anymore, any increase in speed up anymore. So you are not really gaining anything. And then we stop at 16 nodes, and we define that 16 nodes is our optimal node count to run the performance analysis and our production runs. We have recently updated the PDF template in order to provide an additional table that should give us some more information about your planned jobs in production. We ask you to provide what we call the workflow parameters for the Scratch jobs, in the sense of number of jobs that you can run simultaneously, and the work clock time, the typical one of your jobs, plus which is the expected job size for your submissions. In this case, for instance, it will be 16 because you have shown that 16 is the optimal size. And the memory per node that you will be requesting. If you don't know that, of course, it will be at most the memory available on Pittsdiant, which is 64 GB per node on the GPU nodes. the maximum number of input and output files, and the maximum number of files that you access simultaneously. This is also important. And last but not least, the largest file sizes and the library used for I/O, and the maximum number of size and files that will be that you will put on the Scratch file system at the same time. This will also give us an idea of the impact of your simulations during the production runs. So this is again an extract from the PDF template for submitting the national call proposals. And that's an example of a demanding project with a lot of tasks, a lot of simulations using HDF5 as I/O library, and having as maximum size of all files at a certain point on Scratch, like 14,000 gigabytes. So it's a very demanding project. Now, the project in the example above, you can see there are two columns with the label first and second task, because in this example, we assume that we develop the project in two tasks, and that will have to be reflected in the project plan, the section in the template. And two sets of parameters are then provided for each task, one for each task. But we need just one for the overall usage of Scratch, because we are interested in your overall usage among all the different tasks at a certain point in time. Now, the next step is the performance analysis. By this, we mean something that you perform with the Cray performance and analysis tools, which we call CrayPath, as the acronym is showing. In order to do that, you need to recompile your code with these tools. And this is done just by loading a module. The module is called perftools-lite. Then you need to rebuild your code. And we ask you to contact us if you have troubles doing that. In case of a supported application, so a scientific application that we list on our user portal, then we provide the instrumented executable. We provide an additional module path with some additional modules that are targeting this instrumented executable. So you need just to add this, and then you will find it. Second step, you run this instrumented executable. At the end of the run, you will get a report file. So in order to run, you need to use the optimal node count that we have selected from the benchmarks. So we have done the scaling benchmark. You selected now 16 nodes, and then you run this instrumented executable on 16 nodes. You need to take into account that the performance tools of Cray add an overhead to your simulation. So you need to increase the wall time in order to take that into account. Finally, once you get the results, you will get also a report file. The tools will add a folder in your working folder, in your working directory. And inside that, you will find a file called runtime.rpt, like report. We ask to extract a small summary out of this with a command grep that is reported in the slide. And then also to attach the report file runtime.rpt to your submission of proposal, to your proposal submission. This is an example of a summary extracted from the report file runtime.rpt using the grep command that I pasted in my previous slide. It shows you the date and some information on the nodes, plus some information on the runtime and the high memory watermark. Now, last but not least, the resource justification. So this is very important. This is the request for the annual amount of node hours that you plan for your project. Now, the node hours is simply calculated as follows. You multiply the number of nodes by the wall time expressed in hours. That's it. Since we say that CrayPath adds an overhead, you cannot use the timing of the CrayPath experiment to compute that. Instead, we need the optimal job that we performed in the scaling curve. So we need to clearly link this request with the node hours that we have been used in the representative benchmark. So in our example, the optimal job was running on 16 nodes. And in the table, we have shown that it was taking 210 seconds. Then we do this simple calculation in order to get the number of node hours. So the number of nodes multiplied by wall time expressed in hours. So it turns out to be 0.933. I just truncated the periodic digits, node hours. So this will be the base in our breakdown of resource request for the calculation of how many node hours we will need in our annual request. In this section, resource justification, you also provide a request for project storage based on the I/O pattern of your performance report. So requests such visualization, pre-processing needs, and development and debugging go in this section as well. Let's switch now to the praise tier 0 calls for proposals. So far, we have talked about the national call for proposals and the requirements. The technical report is partially done in a similar way also in the praise tier 0 calls for proposal. Here, the template is different. The template, the proposal template, is available at the link at the bottom of the page on the praise research infrastructure web page. And it is called project scope plan. Now, in this template, you have some technical parts that are software and attributes, data, which means management plan, storage, analysis, and visualization, and the performance of software. So let's go through them. The software and attributes is meant to describe all the codes that you use in the proposal with a justification of your choice and description of possible alternatives. You should also describe particular libraries that are required by the production and analysis software that you use. So the algorithms and the numerical techniques that you employ, the programming languages, the parallel programming models, for instance, MPI, OpenMP, pthreads, and so on and so forth. And finally, the I/O requirements and strategy in terms of how many input files, restart files, output files, the frequency of the I/O, the read and write size, all these details. The data part, it shows the management plan, the storage and analysis and visualization requirements. So you need to provide a data management plan with the I/O requirements. In particular, we are always interested in knowing how you will be moving the data from the computing center to your local premises, to the local cluster, local lab, or whatever. So this is vital because you cannot keep the data on scratch. You cannot keep the data longer than your project expiration on the CSCS storage side. So this is the most important part in the data management. Data analysis and visualization also is required to highlight exceptional I/O requirements. And the Phoenix Research Infrastructure resources. So ICI project, you see the link at the bottom here, provides additional resources for computing services, for archive and active data repositories. So if you need additional resources, you should announce your intention to submit a separate request in this ICI dedicated call. And then performance of software. Now, the data that you provide must be representative of the entire workflow of the project. And you should always refer to the main application code used in production. Use software scalability data to choose the most efficient job size, as we showed for the national call for proposals. And keep in mind that software performance must be clearly linked to the resource request. So all data must refer to the systems that are targeted in your production runs. And for any concern, in doubt, always contact the computing center. The strong and weak scalability are the core of this part, the software performance. So you need to explain if either weak or strong scalability metric is not relevant in your case. You start with the minimum node count necessary to run the problem, justify the minimum size if it's not one node, like memory restriction or wall time restriction. And you finish with the maximum number of nodes that is suitable for your application. So you mark this number of nodes, and you mark the number of nodes that you expect to perform the optimal workload in your production project. Now, you plot the time to solution. You can renormalize that, scale that as you wish, but you need to plot that together with putting the data in a table. Or you can plot the speed up, whatever you prefer. It should be clearly stated what are the timings, and we should be able to retrieve these timings clearly, not to extrapolate them from the plot. So that's why you need to plot, you need to put the table with timings together with the plot. So this is mandatory. You can use log plots to spend more orders of magnitude and to make the visualization simpler. So this is an example of the extracted from the template for T0 calls for proposals. So on the right side, you have the example from the template, but you see in the table, there are n prop mentioned. So please, in case you report data for Pittsdind, use nodes instead, because you are given an allocation for the preparatory project with node hours, nodes. So it makes more sense to put nodes, and it's much easier for us to evaluate your proposal. Then also here, you evaluate the efficiency on a certain number of nodes n as the ratio of the ideal time to solution divided by the real time to solution. So in the formula I put with Greek letters the ideal, the tau is the ideal time to solution, and the t is the real time to solution. The ratio is equal to the ratio of the real speed up, s, at a certain number of nodes n, divided by the ideal speed up, which grows linearly. So it is n divided by n0. In this case, n0 in the table that we have here would be 4,800 processors. Now, let's go through an example step by step. So a small benchmark of the CP2K code is provided online. And this example simulates the dynamics of a water box featuring 256 molecules. The basis set, the input file, the potential, and the Slurm batch script can be downloaded at the link that I provide here. And it's available also on the user portal with the full description, together with the Slurm template script to run the strong scaling experiment. So in this script, there is the constraint GPU, which runs on the hybrid Cray XC50. And we use one MPI task and 12 OpenMP threads. The script writes an output file with the Slurm job ID in the name, so it's easy to retrieve that. And it appends the wall time to a log file that is called slurmjobname.log. The full description is available at the link on the user portal that I provide here. Now, the example technical report goes on to the scaling experiment. So the small size of this example allows us to start the scaling test on 2 nodes. We don't go at 1 node because it would take more than an hour running. So due to wall time constraints, we limit to 2 nodes. Then we submit larger scaling jobs, and we double each time the number of nodes that we use. The wall time on 2 nodes then is the reference timing that we use to compute the speed up. The ratio of the speed up values, so the one of the benchmark with respect to the ideal, the linear one, will give us the parallel efficiency. And then we check which speed up we obtain at each step when we double the size of nodes. And we continue until we reach more or less 50% parallel efficiency. So the log file that we saved with this example reports the Slurm job ID, which we'll also ask you to report. And then this gives us the possibility to estimate the optimal job size for production jobs, that is 16 nodes in this case, at 61% of parallel efficiency. So I've shown that from the project template. Now, that would be more or less the way you would present the data. There is a table with the timing, the speed up, the job ID that we use to compute each of these timings. And then on the right side, we have the scaling plot with a representative benchmark in red and the ideal, the linear speed up in the dotted line. And the formulas to compute the speed up and parallel efficiency on the bottom. So we choose then 16 nodes at 61% parallel efficiency. And we go now to the next step of the performance analysis. So with the CrayPath tools. Now, we use 16 nodes to run, and the results of this run will be a folder called RPT files that will hold the runtime report, runtime.rpt. The report file is inside a folder that you will find in your working directory. And the performance report will be also appended to your Slurm output file. So if you cannot find the runtime.rpt, you can still scroll down your Slurm output file and you will find the same report. Since CP2K is in the list of the supported applications, we provide the instrumented executable upon request. You can find a list of supported applications at the link to the user portal at the bottom of this page. Now let's go then through the steps. We update the module path in order to have the instrumented module file CP2K. So we do load the module.gpu And then we add this common module use and the link that has been provided by CSCS staff. You can find this, this link also on the user portal. Then we load the additional CP2K module file with instrumented executable that is available. And I also export an additional environment variable. This is called path article stack. Now, since I mentioned that CRAPath tools, they add an overhead to the simulation, so we need to increase the wall time to perform this job, we can also reduce this overhead by defining this variable path article stack. So this limits the memory and time overhead. The smaller the value, the smaller the overhead. The default is 100, and 0, you disable tracing. So I put 10, for instance, in this case, which is a good compromise. Now, the folder RPT files with the file runtime.rpt will be created under a folder named cp2k.psmp, which is the name of the executable, plus some digits. So this is a typical way of CRAPath creating a folder in the local working folder. And you can retrieve then the summary using the grep command that I put here and attach the runtime.rpt with the Slum job ID. Now, this is again the example of what the summary report would look like. For a full report file, you can look at the link at the bottom of the page. And last, resource justification. So as we said, we need to clearly link the request of node hours with the node hours used by the benchmark. As I said, node hours are just the number of nodes multiplied by the wall time expressed in hours. And since CRAPath adds an overhead, we cannot use that timing, but we use the initial optimal timing on 16 nodes. Since the scaling benchmark then is short with a small number of iterations, we need to estimate how many additional iterations we will need in a production project. And the project plan might also have multiple tasks, so we need also to add that into account. The annual resource request will need to sum up all the amounts of node hours for the different tasks. So let's see that in detail. Again, we start from the optimal job that consumes 0.933 node hours. As I said, 16 nodes multiplied by the wall time expressed in hours. Then in the breakdown of our resource request, we will mention this timing, which will be the basis for the request. And then we add, for instance, in this example, 2 columns with 2 tasks. We add the simulations that we plan to run in production for each task, the iterations that we need to run for each simulation, and then the node hours per iteration are exactly the amount that we reported in the benchmark, 0.933. We just do the multiplication, and then we find out for each task the total amount of node hours that we will request. And the total request will sum them up to be in total 46 and 665 node hours. Here, there is a small rounding error because it would be 6, the last digit, but it's not a big issue. It depends on how many digits you consider in the node hours. Since we put here 933, I did the calculation with that one, so that if you do the calculation again, you can retrieve the same number, because otherwise it's a bit annoying to have discrepancies. Now, this was the national call for proposals. You would do a similar thing for the praise tier 0 calls for proposals, with just skipping the performance analysis with CRAPath, which is not requested. But the scaling and the linking of the resource request to the scaling is also requested in the praise tier 0 calls. An additional thing that you need to take care in the tier 0 call are the so-called technical guidelines for applicants. So on PITSDINT, there is a file, a PDF guideline file that is available at the link reported on this slide, where you can find all the relevant technical data when you submit the proposal for PITSDINT. Now, since developers and vendors scaling plots do not necessarily reflect the actual code behavior, the scaling benchmarks need to be representative of your study, and they need to support the resource request on the target tier 0 system. So in this case, we're talking about PITSDINT. Then if you apply for a praise project with PITSDINT, it is mandatory that you do a preparatory access and you perform the scaling on PITSDINT. And last but not least, some numbers of these technical guidelines for PITSDINT. In general, in the praise proposal, you are asked to put some core hours, while on PitStint we do every calculation in node hours. So there is a conversion factor, which is 1 node hour is equivalent to 68 core hours. You can do all your benchmarks in node hours, and in the end, for the final request, you just multiply that by 68 to retrieve the hours that you put in the praise form. The maximum wall time on PitStint is 24 hours, and the minimum node count for praise project on PitStint is 6 nodes. So take that into account. The technical data is a must to be provided on the GPU partition and to use the GPU accelerators as well. And the most important point, the scalability and the performance must justify a resource request of at least 1 million node hours. As I said, all technical data must be node hours. Memory per node is 64 gigabytes, and there is a scratch soft quota of 1 million files. Last but not least, the storage, because in the praise form, you need to request storage for work, which in PitStint means project, maximum 250 terabytes allowed and needs to be justified. Home storage, which is maximum 50 giga per user, and we don't provide any archive, so please don't ask for that in a praise project for PitStint. Finally, we have some useful links about the what I've been talking about. And I think I will stop the recording now. We are at 40 minutes. And I will be able to take questions in case you want to raise your hand and put your questions. So I thank you for your kind attention.